estimating this by this, and dx times uk power lp power p. Okay. So this p upon 2 square will be a constant times c, so let's again call it c. So what is going to remain inside is omega, not omega, but R2, because our domain is the full space R2. So the square of this is going to be uk p minus 2 times gradient of uk square and dx and times uk lp norm of the p actually. So this is what that you're going to get actually. Now if you carefully look to this is precisely the definition of the L over P is. By the way, I must write this 2 over P everywhere. So there will be this 2 over P. So if you look this guy inside, so this is precisely the definition of N of K is. So this will become a constant N of UK raised to P by 2 times UK, P and LP. Okay? So I would say that this is less than or equal to UK, P plus 2 and LP plus 2 naught. So this is what the final inequality that you get. Okay? And if you think this is a bit messier, just keep on looking at this and keep your notes in front of you and everything will make sense to you. Okay, so on this side now, on this side of the final inequality that I have got, I would like to apply what you call the Young's inequality. And what version of Young's inequality? This version of Young's inequality. AB less than or equal to epsilon times A power P plus C epsilon times what do you call P prime. Okay. Finally. So if on this side I apply this Young's inequality and I choose the constants in such a way, so for example if I choose P to be, so this is P over 2, so I'm choosing for example 2 over P to be my P actually. So if I choose my P to be 2 over P so that this term goes away, okay, and obviously if you are choosing say for example P to be 2 over P, then your P prime would be something in the terms of the P actually. Okay. So I want to estimate this in such a way that this becomes what N of, what do you call, N or epsilon of N of UK, okay, plus C epsilon, like this is something that you can figure it out for yourself, is that okay, what exponent P and P prime should I choose so that this inequality becomes this actually. Okay. You just have to think for exponents. LP, you have a P, so your P prime is basically going to be 2 over P minus 2, so you're going to have a P square over P minus 2. So this is something that you're gonna get actually. Okay. And all of this is an estimate on LP plus 2 and what do you call LP plus 2 power P plus 2. So this is now, what was our key equation? You know, the equation that was satisfied by UK. So it was 1 over P duk. I can write it more explicitly. So d by dt of uk raised to p lp, okay, plus nu n of uk plus 4 mu p minus 2 over p square, okay, p over d by dt, p minus p square of m of uk equal to I1 plus I2. So if I substitute these estimates, so if I substitute, for example, the estimate for I1 and I2. So what were the estimates for I1 and I2? So the estimates for I1 and I2, so the estimate for I1 was C times of, what do you call, P minus 2 square by mu and UK P plus 2 and LP plus 2. Okay, this is what that you're going to get. And if you wish, actually, you can multiply this constant here, but then you can call all of this stuff as a constant C actually. Okay, so there was some constant, you know, in I1, estimates for I1, and this constant, everything multiplied by, let's call that again constant actually. C plus, what do you call, plus I2 was estimated by the LP norm of Fk, okay, times UK LP norm of P minus 1. Okay, this is what that you're gonna get actually. So everything is same, estimated I1 and I2, and I got this actually. Now for this UK P plus 2 and LP plus 2, we have proved this estimate actually. So let's substitute it. So if you're going to substitute this estimate, so your thing will become, what do you call, so this is going to be C epsilon times of N of UK, okay, plus phi epsilon times of UK power LP and P square over P minus 2, okay, this is what that you're going to get, plus this last term, which is plus, you know, this last term here, okay. So what you're going to get now, I can do what? So on one side, I have this object, okay, and on other side I have this object. So what I can do, let's call this C epsilon. So let's take this term on this side. And you're going to have a mu minus C epsilon times N of UK. So let's give it a name, a constant C, or maybe any constant C. And let's call C epsilon as a constant C. So the final version, that is the final version that you get, is going to look like this actually. 1 over p by dt of uk power p plus a constant, let's call it C1, and of uk plus 4 mu p minus 2 over p square times m of uk less than or equal to some constant times, obviously that constant depends on epsilon, it's just a constant, let's give it a name C, uk power p square over p minus 2 plus fk times, and it's LP norm, times uk and LP and p minus 1. Okay, so this is the inequality for d by dt. So this is one of the crucial inequality. Now, using this inequality, one of the exercise for you, is to that if you take, say, alpha to be p square over p minus 2, you have to show that if you compute the d by dt of, say, uk power alpha derivative. So you have this inequality, differential inequality for d by dt of uk power p. So if you take this alpha, p square over p minus 2, and then you take, what do you call, then you compute the time derivative of, say, uk raised to alpha, then your task, your exercise you need to show is that you can get this as c times of uk power p square plus 2p over p minus 2 plus fk LP norm and uk LP norm and alpha minus 1. Okay? So in other words, using this inequality, try to deduce this inequality. That if uk, okay, I must write this is p plus l, p plus 2 norm, this is LP plus 2 norm, and this is also, let's simply write p plus 2 norm. No, this is LP norm. This is LP. This must be LP as well. Okay, so you got this differential inequality. So using this, play a trick and try to deduce this inequality. And once you have this inequality, just integrate both sides. You take y of t equal to So, in last inequality, take y of t or yk of t as, say, ukt, okay, LP norm power alpha. Okay? And integrate, so replace, and obviously the alpha you have to remember is p square over p minus 2. Okay? And this term is also present here. Take this inequality, using yk of t, try to write it in the terms of the y. Okay? Try to write it in the terms of the y. For example, this will become dy by dt. This will become something, so if you separate it as say y power say p square over p minus 2, so it's going to be y power alpha plus something, and this will also become 1 over y. So let's try to write this inequality in the terms of the y. So take your yk, try to write in the inequality in the terms of y, and then integrate that inequality from s to t. Then integrate on integrating the inequality, you're going to get something like this. So you're going to have yk of t, yk evaluated at, so if you're going to integrate the inequality say between say s less than t bigger than or equal to 0 and t being finite. So if you integrate it between s to t, obviously the first term will become yk of t minus yk of s, okay, and the other side will become something like this, c times of s to t, okay, and y k plus k yk is going to become p plus 2 upon p plus yk plus fk power alpha and LP norm. Okay, fk power alpha and LP norm. So this is what it is going to become actually. I mean, if you see, this is really in such a form actually that you require. Is in the form. So I have y of t minus y of s, and I have f of y of t. So this is my f of y of t. So it's a exponent function, simple exponent polynomial actually. And then h of t and h of t, it can be treated as this norm. Okay. And once you have this, then what I would like to do is that I would like to take the limit k goes to infinity. Okay. I would like to take k goes to infinity, and once k would go to infinity, so I want that this ukt LP norm power alpha should converge to the u of t LP norm of power alpha. So if I can prove this, that uk of t LP norm power alpha or some power converges to what you call u of t in LP power alpha, then I can take the limit on this side and I can get what I want. I can get what I want actually. So the next thing is really going to show that this u k of t LP norm, does it converge to u of t LP norm as k goes to infinity. So if I can show this, I'm done actually. Because this yk will go to y of s, y of t, this will go to y of s, and this will become y power p plus 2 upon p, this will become y, and for this you already have a result actually. So that's not a big deal. So I would like to show this fact next. So how can I show it? We are almost done actually. So you just have to be a little bit patient. So if you use your energy estimate, so what were my energy estimates? Let's recall them. So these were two my energy estimates. So the U of t can be in H norm can be estimated by the U naught in H norm plus 0 to infinity f of t in H norm ds. So this was my first estimate, and the second estimate was mu of 0 to t gradient of, say, u of s square in H norm dt can be estimated by the norm of u naught in H sense plus 0 to infinity f of t in H norm, or f of t in H norm dt times 0 to infinity f of t in H norm dt. So this is what that you have. So these were the two estimates. So if in this estimate, in the Navier-Stokes equation in u minus uk, so in other words, u minus, so if for every solution of the 2D Navier-Stokes equation you have such an estimate, so you're going to have also an estimate for u minus uk. So using this estimate, maybe one exercise for you to explicitly show is to show if that UK converges to u in phi 0 to infinity and L2. Okay. UK converges to u in C0 to T infinity L2. So what you need to do, just replace this u by, u minus uk, and obviously you need to replace the initial condition by u naught minus uk naught. Okay, and then calculate what you call the L2 norm of it, and then that L2 norm should, take you to the zero. Why? Because you already have convergences. You need to keep in view the convergences of the u naught converges to u k naught, and fk converges to what you call like this guy converges to this, and fk converges to f actually. So when you're going to calculate, for example, uk minus u and its h norm and its square and then its integral, then you need to square this side and then integrate, okay, and then instead of u naught you're going to have u naught minus uk, and instead of f of t you're going to have fk minus f, and fk minus f and u naught minus uk naught in the suitable sense goes to 0 as k goes to infinity. So if this side go to 0, then the square of the integral would also go to the 0. So in other words, I just give you what we call a rough sketch. You need to just make it rigorous. Is that the uk converges to u in C0 to infinity in L2 norm, and since you have this estimate, so you can also replace u minus uk here, and using these two convergences you can show that uk also converges to u in what do you call L2 okay, 0 to infinity with in H1 norm. Okay, so I need to just say what would be the norm on C. So the norm on C is going to be the supremum actually. So what you need to do, you need to take the supremum of the u square on this side, okay, and then integrate that actually. And you need to show that, okay, using the convergence of u naught to uk and fk to f, try to prove these two actually. So it's a good exercise actually. That if I use this inequality, next, if I use this inequality and replace u by what do you call u minus uk, where u and uk both are the solutions of Navier-Stokes equation, so they both satisfy and hence their difference should also, so their difference should also be a solution, and then their difference should also satisfy what do you call such estimates. So the one of the estimate that you're going to get is u minus uk in h norm is less than or equal to, what do you call the uk naught minus uk plus s to t, maybe 0 to t, and fk minus f in h naught. Okay, so this is what that you're gonna get. This is also in h naught. And keeping in view the convergences that we know about uk and fk, so what were the convergences? So the uk converges to uk naught in LP intersection L2, and fk converges to f in L infinity and also in L1 sense actually. So in other words, using these two convergences, what can be shown roughly that this guy goes to 0.